Cool. Thank you, Hendrik. Thanks for the introduction and thanks for having me. It's great to be here. I'm very excited to share my favorite topic, experimental nuclear astrophysics, with you. So let me share my screen. First of all, as Hendrik mentioned, there's lots of opportunities for students at MSU. So I wanted to put some information on a slide, and this will be posted so you can get all the links and everything you need. The main point is that we do have many different programs, especially for summer research, but also we have one summer school that is a 1 week long program. If you're not sure if this is for you, maybe this is an opportunity to learn about the field. And yeah, if you have any questions or if you're interested to apply and you just want, just some help or just find out details, then feel free to contact me. I have my email here, or contact Hendrik or Anna. And in general, for this kind of projects, we don't require previous experience in nuclear astrophysics. Just expressing your interest is enough to get you started. And the one thing that is useful, again, it's not necessary, but it's useful for anything you do really these days in life, is to have some programming experience. So if you're looking for something a skill to develop on your own, this would be something to do. But as I said, you don't have to. I've had many graduate students. I started as a graduate student knowing almost nothing about programming, and slowly you build the knowledge. Okay, so the topic for today is the nuclear physics of exploding stars. And again, my information here if you're interested to contact me. Before I dive into the field though, even though Hendrik did an introduction already, I put a couple of slides together to kind of introduce myself as well. And so I'm originally from Cyprus. I grew up in Cyprus. Cyprus is down here, it's Europe. And so it's a little island country down here. It's a small country. You can drive from one end of the island to the other in about 3 hours. And it has about 1 million people. It's nice and warm there. It's an island, so lots of ocean. So it was nice growing up there. Then I moved to Greece, and I did my undergrad in Thessaloniki, which is at the northern part of Greece, physics major. And then I moved to Athens, Greece, a little bit further south, where I did my PhD at the National Technical University of Athens, and at a lab there that's called Demokritos. There's an accelerator there, and there's again nuclear physics, experimental nuclear physics research. And after my PhD, looking for a postdoc, I moved all the way out across the Atlantic. We just skipped here in the maps and came to Michigan. So Michigan State is right here at the kind of at the center of Michigan. And so I came here initially as a postdoc for 2 years, and then kind of going through the ranks, assistant professor, associate professor, and now full professor. And as Hendrik said, I served as the associate director for education for 4 years. And now I'm leading the outreach activities of the lab. So if you have any questions about any of these, about education, about opportunities at the lab, about outreach or research, or just want to chat and ask about Cyprus, just feel free to email me. The other thing I like to share is, we're physicists and we like our physics, but we're all so much more than that. And we have our hobbies and our interests. And I like to share some of that because that just makes it a little more personal. And again, maybe some of you have the same hobbies and we can start chatting about that. So in school, I did competitive swimming. I went pretty high. I was in part of the national team in my country. In grad school, I picked up snowboarding. I never skied. Cyprus doesn't have a lot of snow, but I started snowboarding in grad school up in the high mountains in Greece. You can find snow. And now basically I only go when I go to conference. Some of our conferences might be up at high mountains, and that's basically when I go. Unfortunately, Michigan has a lot of snow, but it doesn't have very many mountains. So there's that. I have 2 girls. You can see them here. This is a couple of years ago. And our puppy is not so small anymore now. He's a big puppy. I started running a few years ago, and this summer I achieved a 1/3 marathon, not quite a half marathon, but 1/3. So I'm trying to get to a half marathon, hopefully soon, or maybe next spring. And another hobby I have together with my girls, we like to bake. So this is one of the cakes we made for one of their birthdays. So just something to share. Let's dive into physics. So nuclear astrophysics. Nuclear astrophysics is quite a broad field, and it brings together several subfields and trying to answer questions about stars, about how they are they're formed, how they evolve, how they explode, how the various elements we see around us are formed inside stars. Why do some stars explode and how much light they emit, or now gravitational waves and so on. So these are big questions that we're trying to answer in the field. And to do that, we're putting together a lot of pieces. You cannot do it with just one subfield. So you have the observations, you need astronomy, astronomical observations, and that's your observable. It could be from electromagnetic telescopes, it could be now with gravitational waves or measuring neutrinos. It could also be measuring meteoritic samples or solar system samples in general. So these are all our observables. And then we have to figure out a way to model the universe or the particular stellar environment to reproduce these observables. And so that's where modeling comes in. You have the astrophysics modeling that is trying to reproduce these observables and draw conclusions for how they could be created. And now that astrophysics astrophysics model needs some input. And it's important to have accurate input, otherwise what you're getting out might be incorrect. And so you have to describe the star accurately, the temperature of the star, the density, what kind of ingredients it has already. So all of that goes into the model. And you also need a lot of nuclear physics that goes in, and hopefully through the whole talk today, I will show you what kind of ingredients we're looking at. And so for all these nuclear ingredients, you can either measure them directly in the in the lab. And that's my job as an experimentalist. This is what I'm trying to do, identify what is needed, and then try and go and create an experiment, design an experiment and run it and measure the specific thing that is needed to understand one of the astrophysics questions. Or if it's impossible to measure experimentally, you can either rely on theory and try to have as accurate as possible theoretical prediction, or you can combine the two. You can say, okay, I cannot measure this directly, I cannot get the full answer, but maybe I can constrain it enough that if I work with my theory colleagues, we can together draw an educated conclusion for what this quantity might be. So this kind of gives you a big picture for how the field of nuclear astrophysics works. And as I said, one of the questions that we're trying to answer is how all the chemical elements are formed. So that's why I have the periodic table of the elements here, and this is where we will start the journey today. There are many other questions, but this is kind of what I'll focus on today. Throughout the talk, we organized to sprinkle some questions like you had in previous lectures. And just to get us started with a sample question, just warm up, I will ask Alexa to pop up the first question about the Nobel Prize. There we go. Alexa, I don't know the process here, but I guess when everyone voted, you'll show the answers.
Yes, let's see. They're coming in. I think we have most everyone.
Cool. I guess everyone can see the answers. So if you missed it, Nobel Prize in Physics, or all the Nobel Prizes, were announced last week. And the one for physics this year was on the topic of black holes. So the discovery of a black hole at the center of our galaxy. And it went to 3 people that I will mess up their names right now, so I will not attempt to say them, but you should look it up. The topic was black holes. Okay, so that was our warm-up. Let's dive into nuclear astrophysics. As I said, the thing I'll focus on today, even though this is not the only thing we're looking at, the thing I'll focus on today is how are all these elements that we see around us, where are they coming from? How are they created? So we have the periodic table of the elements, and we can say, okay, there's the various elements, and we can look at the solar system and see which elements we have. But maybe even more important than that, it's not just which elements we have, but also how much of each we have. This already, just looking at the amount of each element, already tells us a lot about how these elements are formed. So for example, here I'm plotting the abundance of these elements, so how much we have from each element. And I should mention, this is a logarithmic scale, so the changes you see here are actually pretty big. And this is plotted as a function of atomic number. So I marked some of the elements. We have hydrogen and carbon, oxygen, and so on, and iron. And you see very interesting structures, right? You have hydrogen and helium are here at the top. And then you have a big deep for the next 3 elements. You have a lot of carbon and oxygen, maybe slowly going down, but then there's a peak around iron. And then keep going down, and we have very little of the heaviest elements. Even at the heaviest elements, if you look at it carefully, you'll see some bumps here and there, and also which are also significant. So all of this, spoiler alert, all of these structures that you see here are all coming from various nuclear physics properties. And so I'll talk about this a little bit later. The other thing I wanted to point out, so these are the elements in the universe. Let's say the elements in the solar system. But the universe in general, we see similar structures, although different stars can be different from each other. So another question, we can make this a lot more personal, right? We can ask, okay, this is what is in the solar system, but what about if I make it personal and ask about what's in myself, what's in the human body? We care about what we eat, right? We care about our history, about where our ancestors came from. Why not ask the question, where do the elements in our body, where did they come from? And also what they are, how much of each do we have? And so we can look at it in many different ways. One way to look at it is, what does the human body consist of? You can say it's about 62% water. There's protein, there's fat, there's a lot of different things. And on average, this is kind of the distribution we have. But we can go even another step after that and try to figure out what kind of elements we have. And before I do the next step, I want you to try and answer the question. Maybe you know it, maybe you don't. Alexa, can you post the next question? What kind of elements, I guess, which element out of all these elements we have over here, which element is not present in the human body? It's just I don't know, either you know it, either or you don't, but I think it's just interesting. And by the way, I don't know the answer to the why that is, but it's just interesting. Okay, so we have 100% helium. Great. As if you know that the other ones are there, then it's easy to guess helium. But yes, that is correct. 100% helium is the answer. And again, I don't know why, if anyone else knows why we don't need helium for our bodies, that would be interesting to know. So yeah, if I put the distribution of elements in the human body, this is kind of what it looks like. You have a lot of oxygen, that's at the top of the list. You have a lot of oxygen, and you have a lot of carbon and hydrogen and so on. So these are a few of the elements. We actually have a lot more. There's there's about 30 elements that you can find in the human body, even either in trace amounts or, of course, more than that. Now, I wanted to create this plot, and I wanted to take the extra step and say, okay, if I plot the same plot here for the elements that we have in our bodies, what would it look like? How does it compare? How much of each element do we have in our bodies compared to what the universe offers or the solar system offers? And maybe it's not surprising that it's very, very close. It's we have a lot of hydrogen. It's right here. The helium is a strange thing. We have no helium, even though there's plenty out there, but we don't have it. But then you see there's a lot of carbon and oxygen, and we use a lot of that, obviously. There's a lot in this region, the phosphor and the calcium and so on. And there's even a peak around iron. And some of the trace elements we have for the heavier masses. So it's just a nice picture to see. It's not just that we're made of the same elements. Obviously, we're made of the same elements. We're part of the solar system, but even in the same amounts. And it's just nice to see the connection, the immediate connection with our environment and our solar system. So this makes the question of where do all these elements come from? This makes it completely personal. I have a look at my my fingernails, and there's a lot of calcium in there, and I can start to think, where did every atom of calcium in my fingernails, where did it come from? And actually it could be that the calcium in one fingernail came from a different spot in the universe than the calcium in another fingernail. So that's and you can imagine the trip for a calcium atom that was formed somewhere in a star and traveled through the whole universe, maybe went through multiple stellar lifetimes and eventually made it to the solar system and made it onto the Earth and made it on you. That's just an amazing journey to think about. So looking at the elements, let's see where they're coming from. So the first few elements, first three, were actually created during the Big Bang. If that's all we had, it would be a very easy periodic table to memorize, and we wouldn't actually be here to consider that. So that would be very simple. But everything else is made in stars. Now you can ask the obvious question, how do we even know that? How do we know that all the elements are made in stars? Maybe they were made at the Big Bang. Maybe they always existed and we just see them. Well, the answer to that is the element technetium. At least the first answer came from the element technetium. You can see technetium here is white, as opposed to most of the other elements here are marked in black. And there's a reason for that. It's not a typo or anything. There's a reason for that. All the elements on this chart that are marked with white are the artificial elements, and technetium is an artificial element. It means that if I go out on Earth or anywhere in the solar system and I take a sample, I should not find any technetium at all, because it's relatively short-lived compared to the age of the Earth. And so anything that was created at the time the Earth was created, anything that was here at the time the Earth was created, just decayed away. So that was an observation done in 1952 by an astronomer called Paul Merrill at Mount Wilson Observatory. And at the time, it was not completely clear if the elements were made in stars or at the Big Bang. There was a whole debate going on. And so you can imagine his surprise when he turned his telescope looking at a specific star and he saw lines of technetium. Just to get an idea, if we say that the Big Bang was a few billion years ago, and you'll see something that is only should decay within 4 million years. That's the half-life of the longest lived technetium isotope. Then if you see it there, then immediately either you think your measurement is wrong, I'm sure that was the first thought, but once you convince yourself your measurement is right, then it's immediately either the technetium half-life is wrong, or the star itself is making technetium. And that's actually the case. The star itself was making the technetium that Paul Merrill was observing at the time. And this was kind of the first proof that the elements, at least these heavier elements, were made inside stars. And this opened the whole field, the field of nuclear astrophysics, which is trying to answer this question: what kind of stellar processes are making these elements, and how can we create a model or multiple models that will reproduce all the elements that we see around us. So maybe let's take another quick break here and ask the next question. Alexa, you can go ahead with the number of elements. So you can see the answers here. The majority is right. The number of elements that have been discovered up to now is 118. It was on one of the previous slides. And they were recently meaning 3 years ago, I think, they were named all the way up to 118. There are other elements, heavier elements, that have been observed, but because they haven't been confirmed yet by multiple groups, we cannot claim discovery just yet. Okay, back to our topic, talking about elements. Really, if we think about it more carefully, the question of where the elements are made is not the right question to ask, because each element is made of multiple different isotopes. I'm sure you heard about that from previous lectures. And so each of the isotopes for every element could be made in a very different stellar environment. So here, excuse me, here I have the example of molybdenum, just blowing up the central part of molybdenum here on the nuclear chart. In case you're not familiar with it, we are plotting here the number of protons versus the number of neutrons, which means that every row on this chart would correspond to a different element. So row 42, which is the atomic number of molybdenum, would correspond to molybdenum. All the black boxes here correspond to stable isotopes, and then the colored ones correspond to unstable isotopes. So in general, the goal is to figure out where all the stable isotopes are coming from, because typically when you look at a star, you're not looking at what's happening right now. You're looking at kind of the leftovers after all the processes are done. Okay, so if I, just as an example, if I look at the different isotopes of molybdenum and I want to see where they are made, we don't know everything for sure. There's a lot of question marks here, but we know that they're made, or they have the most significant contributions are coming from particular processes. So for example, the most proton-rich ones, 92 and 94, are most probably formed in some kind of supernova. I have here type 2 or type 1a, it doesn't matter, but it's some kind of supernova. These middle ones are formed in AGB stars, most probably. I think this is probably something that we know pretty well. And then the last two, again, it's a big question. There might be in neutron star mergers or in supernova, or you have contributions from both. We don't really know yet. But you can see that different isotopes, even from the same element, molybdenum, they come from very different stellar environments. So in terms of looking at how all these processes work in the nuclear physics, I wanted to show you just the simplest, most basic example of trying to form new elements in an astrophysical environment. And I will do that by trying to get from hydrogen to helium-4. Helium-4 is one of the most stable nuclei we have, and it's let's say you are in an environment where you only have hydrogen, then what kind of nuclear processes would have to take place in order to go just from hydrogen to helium? And you can kind of extrapolate and try to imagine the complication and the mess that you would have trying to get even heavier than that. So in this assumption, let's say we are in an environment where you only have hydrogen. And so there are my two hydrogens, basically just two protons flying around in the environment. So you can imagine that the easiest thing to do is having those two protons fuse together, and you would make a helium-2. So a nucleus with two protons and nothing else is called helium-2. So I go to my chart, here's my hydrogen, and helium-2 would be right above it, right here. And you see it's kind of an empty white box. And that's because helium-2 actually is what we call unbound, and immediately it will break back into the two protons. So we haven't really made much progress. You are in an environment with just hydrogen, and you still have just hydrogen and nothing really happened here. Well, nature figured out a different way to solve this problem. And this is in what is called a weak process, where at some point, every once in a while the two protons are fusing together, one of them actually is converted into a neutron. And there's some other particles flying around to have all the conservation laws apply. And so if this happens, then you go from hydrogen 1 to hydrogen 2. Now you have one proton and one neutron. You didn't make a new element, but at least we made some progress. We didn't just stay where we were. We made some progress. We made something a little bit heavier. Now, the fact that this reaction here is not very easy to do, it's actually very, very hard to do. You only have one such reaction every few million years or something like that. The only, we are lucky that this is so hard to do. This is the reason our sun keeps burning today and will burn for about 10 billion years. If the first reaction was possible, then everything would just go very quickly. You have so much hydrogen, and if it's just easy to fuse two hydrogen nuclei and proceed and make something else, then everything would just be done in probably in a few seconds. There will be an explosion because there's nothing stopping from this process to happen. And so the fact that this reaction is so slow is the reason that our sun just burns its fuel slowly, and we're here to look at it and wonder about it. So once we do build our hydrogen-2, it's called deuterium, by the way, then it's very easy to grab another proton from the environment. There's a lot of protons, and make helium-3. And there you go. We just made a new element. We went from hydrogen and we made helium-3. Now our goal was to get to helium-4 because that's kind of a more stable and system. And so the way to get there is once you make enough helium-3, it could fuse with another helium-3 from the environment, made in the same way, and eventually make a helium-4, shooting out some protons. So this first part is what I wanted to focus on, but you can kind of see with little balls here of protons and neutrons how it goes, that you can fuse, you can add protons, you can remove neutrons, you can fuse things together to build heavier and heavier elements. And this is how the whole thing works. It's just that it gets more complicated. Obviously, the heavier you go, you have many more options, the reactions get harder and harder to do. And so, but this is kind of how the whole field of nuclear astrophysics works. You have to look at these details of how the reactions between different elements and different isotopes will take place. This, by the way, is called the proton-proton chain. And if I put it in the big chart of nuclei, it would be sitting down here, just going from hydrogen to helium. In very similar reactions, you can build all elements going all the way up to iron. Again, it's environments where you have a lot of helium or a lot of hydrogen. And so whatever you build, whatever new nucleus you make, it would be easy to capture another proton or another helium, we call those alpha particles, and just slowly go heavier and heavier. And some of these reactions are easy and some of these reactions are hard. And so a lot of research is going into understanding these reactions. That's one part of the experimental nuclear astrophysics. At iron is kind of special. You saw earlier, we have a peak around iron. Iron is special because as you go heavier and heavier, it just gets so harder and harder to get a proton and squeeze it into the nucleus, because as the nucleus is heavier, there's a Coulomb force, Coulomb repulsion between the two charged particles. The proton is charged and the nucleus is charged. Another way to think about this is in terms of energy. In a stellar environment, the lighter reactions, all these reactions here, release energy, and so they help balance the star, they help with its evolution and just kind of maintaining its stability. But if you go to heavier than iron, then those reactions eat up energy, and so they go in the opposite direction. They don't help with balancing the star at all, they actually help just kind of destroy the star. And that's why iron is kind of the end point, or kind of a magic point there in nuclear astrophysics where things have to change. And the way they change is that for heavier nuclei, you need neutrons. You need to have an environment which has a lot of neutrons, and through neutron processes, you can form the heavier elements, and we'll see examples in a second. There's also another process that doesn't involve neutrons. It involves gamma rays that I'm not going to go into detail, but you just have, basically, you have created all the heavier elements, and during an explosion, when the shock front of the star goes through these various layers of the star, then it could excite nuclei and start shooting out protons and neutrons, and you can go through this P process. Okay. So this is all very, let's say, qualitative, and with the little balls for neutrons and protons trying to build the different reactions. In reality, once you get into these processes, things are very complicated, and you need to use simulations, you need very fast processors, you need supercomputers to actually try to simulate what's going on in the star and try to see what kind of nuclei are important, what they're doing. So one example is this simulation here. That is done by Jonas Lippener, who here simulates what we called in the previous slide the R process. It's called the rapid neutron capture process, so it involves neutrons again. And let me go back. So you will start with some nuclei that exist in the star here, the lighter nuclei, and you see as neutrons are added, you kind of go through a zigzag going upwards on the chart. I'll pause here just to see a couple of things. Pause a couple of seconds earlier. There you go. So you see these lines, horizontal and vertical lines that are shown on the chart of nuclei. These are important lines. This is what we call magic numbers. Nuclei which have that number of neutrons and that number of protons actually are more stable than their neighbors. And so when the flow in the star, when the flow of matter goes through those particular numbers, then it kind of stalls. It just likes to stay there. It doesn't like to add more neutrons or decay or do anything. It just likes to stay there. This is actually pretty significant because you just accumulate matter around, you see the red colors here, you accumulate matter around those magic numbers. And that matter, if we go to a little later time, you can see this propagates as everything decays back to stability. This accumulation of matter, these red regions, propagate all the way to the stable isotopes. You can still see it here and here. And this is our abundance plot again, similar to what you saw early in the talk. You see little peaks that are formed that come exactly from these magic numbers. This is, if you think about it, an amazing connection. These are magic numbers. This is a very basic nuclear physics property that these nuclei have, and it translates it into a macroscopic observable, these peaks in the abundance distribution when you look at a distant star. So you see immediately the one-to-one correlation between those two fields. So going back to our the nuclear physics, diving into the nuclear physics, we're trying to understand how these processes work. And so as a nuclear physicist, I need to identify what is needed and then figure out a way to measure it. So for example, in the R process, to figure out what is needed, I have zoomed in here into like where the R process goes. And the things that are needed are neutron capture reactions. So what's the probability for a nucleus to capture a neutron? And what we call beta decays, just the nucleus decaying, switching one of its neutrons into a proton. these are the two main things that we need. We need a few other things, but these are the most basic things we need are those two ingredients. We also need some fission. Again, I'm not going to go into the details of all of that. If anyone's interested, you should let me know. So once you figure out what you need, then you need to go and find a facility that can provide the beams that you need to measure this. If I look at the chart of nuclei, you see all the stable isotopes are out here, and the part where I should be measuring is all the way out here. These are isotopes that are very short-lived. They only live for a few seconds or a few milliseconds. So you need to have a very special facility that can provide these nuclei so you can do your experiment with them and study them. And this is what we're doing. This is our specialty. At Michigan State, we create radioactive beams, beams of nuclei, beams of isotope that are radioactive, that are exotic. So we can also call it exotic beams. So again, this is where where the facility is. This is kind of the building. If you pass outside, you see there's a lineup of scientists waiting there to do their experiments. No, this is just our open house. There's a lot of interest actually in the community around MSU to come and visit the lab. We give tours. It's a point of pride, I would say, to have such a large nuclear physics facility on campus. And it's a large lab. We have about more than 850 employees, large group. So this is just another group. Nuclear experiment theory and accelerator science. We have 45 faculties, so lots of different options. I tell students that in terms of nuclear physics, if you walk in the building, there's probably an expert for anything you are interested in, any question you have. Yeah, large numbers of students and postdocs and undergraduate students at any given time. So without COVID, it's a very lively environment to work. So here you can kind of see the current facility and how it produces its beams. We have 2 cyclotrons. And so you would get the beams of particles injected in the center of the cyclotron. And as they go faster and faster, the radius gets larger and larger. And at some point when you have accelerated at the energy that you're interested in, then you can extract that beam and then guide it into your experiment. The speed of the beam, just to get an idea, is about 50% the speed of light. So these particles go pretty fast. And actually here I'll take another break and have you think about what, Alexa, pose the next question, please. How long would it take for this beam, 50% the speed of light, how long would it take for this beam to travel around the Earth? Order of magnitude. If it's, if you think it's an hour and it's actually half hour, just put an hour, just order of magnitude. Yeah, good guesses. The majority is right. Again, it's of the order of a second. If you do a very rough calculation, the radius of the Earth is about 6 kilometers. So that's 6 × 10⁶. If I do 2 pi times r to get the circumference of the Earth, you get at about 10⁷. Speed of light is about 10⁸. And so if you do all the calculations and all of that, you'll get about a second. It's about half a second, actually. It goes around the Earth twice in a second. Okay, so the way the lab produces the radioactive beams, you have to start with a stable beam. You cannot do anything else. This is what's available on Earth. And let's say we will start with a krypton-86. That's one of the stable isotopes. And our goal is to produce nickel-78. That is quite an exotic isotope, actually. So you would get your krypton-86 accelerated through the 2 cyclotrons that we have here. And now out of here, that's the 50% the speed of light, or in terms of energy units, we say it's 40 MeV per nucleon. These are the units we typically use. Then we shoot that beam on a target. And at these energies, the dominant reaction you would have is called a fragmentation. So that beam literally just breaks into pieces. And you can have many, many pieces coming out. It will look something like this. So your krypton-86 is somewhere there, and it will produce all of these isotopes, and the colors indicate the intensity of each isotopes. This is a bit messy, I'll say. So if as an experimentalist, what I'm interested to measure in this is nickel-78, I'll tell you I cannot measure it because my detectors will be completely overwhelmed with everything else that's coming in together with the few nickel-78s. So we have to clean it up. We have a pretty good filter to do that. It's called a fragment separator. That's this thing. And so there's two stages to the fragment separator. If I look halfway through the separator, this is what you would get. Already we excluded a lot of the isotopes, but there's still a bunch left. And then through the second stage of the separator, you end up with a little group of nuclei right around nickel-78. It's not a pure beam. You still have some additional isotopes coming in, but we can work with that. We have very sensitive equipment that can, event by event, nucleus by nucleus, with accuracies of a few nanoseconds, you can measure and say, okay, this is what came down the pipe, this is what came into my detector system, and this is when it came, and just identify everything event by event. But you have to have a small number to do that. You cannot do it with the millions of events. And so once you have your nucleus, then you have to guide it into an experimental area. And we have many, many different experimental stations in the lab. If you come for a tour, you will be able to see all of these. Is there a comment, question? I hear some coughing. Is there a question? No, we're good? Okay. So yeah, you can guide it into many different experimental stations to do experiments. And I will not try to describe everything. I will just try to describe my own research. So if you're interested, you should feel free to contact me and we can maybe have a summer research or something. So this is my group. It's a relatively large group. Typically, experimental nuclear physics groups are of the order of 5, 6, 7 people. So this is on the larger side. I have undergraduate students, I have graduate students here, postdocs, staff members. The things we measure we're trying to measure these astrophysical reactions that are interesting to understand how the elements are formed. We study also beta decays. I mentioned earlier that those are the two main things that are important. There's a lot more, but in terms of the art process, these were a couple of the important things. And we extract nuclear properties. To do this, we develop new equipment. We have to test it. We collaborate with our theory colleagues. So there's a lot of discussions and a lot of interactions with our colleagues to try and do these experiments. If you're interested to see what our equipment looks like, these are just some examples. This is the heart of the group. It's called the SUN group because we are using the SUN detector. It's a large volume detector that measures gamma rays. So the idea is that either you put a target right at the center of the detector, and then you shoot a beam at that target, and you look at reactions happening, and you measure the gamma rays coming out of the reaction. Or you get a beam and you implant it at the center of the detector and you watch for the beta decays happening. And then again, you look at gamma rays coming after the beta decay. So it's a very efficient gamma ray detector. The rest you can see here are kind of accompanying equipment. My group has been very creative in naming our detectors. So you see we have Santan here. This is the tape system to remove contamination. We also have sunscreen that I didn't put on the slide here. And yeah, there's this detector is kind of a creative design that uses fiber optics to collect the signal from the detector and kind of read it outside of sun because this hole there is very small. Oh, just to get a sense of size, this is 16 inches, just to get an idea. Yeah, so this is, if you like equipment, this is what our equipment looks like. And It's in terms of running experiments, this is actually my favorite part as an experimentalist. This is my favorite part. Just get the whole group together, and it's a tough time because no one sleeps, and there's a lot of things that need to happen with a very sharp deadline. Experiment starts on on Monday. You better have everything ready. And then we run 24/7 for a week. So this is an intense time, but you can see the whole team just working together, and it's a very educational and interesting time when we run experiments. This setup here is actually when we moved the sun detector to Argonne National Lab. So we do experiments at other facilities as well. So this is at Argonne National Lab when we just installed it on their brand new beamlines here. So here's sun on the beamline, and this is sun behind it. So here I will have the next question, I think. Let me see. Yes, this is our next question. What are the most important things for running an experiment? So, yes, the answer is all of the above. You need everything. You need teamwork. There's no way to run an experiment with just a single person. It's so much work, and it takes so much effort and time and so on. No one person can do it on their own. You need to prepare, because if you have beam on a specific day, then you better be ready. You don't want to waste beam. This is a precious beam time that many people around the world are fighting to get that 1 week of experimental beam time. And so you don't want to waste that. So you better be prepared. You better know what you're doing. And that's where, again, you have experts around. If you don't know something, you can ask someone else. We have different groups collaborate with different expertise. And I'll say snacks are important. I've run experiments where there are no snacks and there's no energy for anyone to run. So this is an actual picture of our experimental station where we run. Well, the equipment is in the experimental halls and we're sitting outside. And so this is what it looks like at the desks where we're sitting and collecting data. And this was actually a healthy day. Usually it doesn't look so healthy. Okay, so in the last few minutes or so, I want to talk about the future. And the future is a new facility that we're building. It's almost complete. It's AFRIB, the Facility for Rare Isotope Beams. So right now, if I look at specifically for the art process, this is kind of roughly where the art process will go. And the blue color here shows you which nuclei are accessible today with the current facilities. And you can see that the majority of our process nuclei, we don't even reach. It's maybe we're touching a little bit here and there, but the majority we're not there. And that's why we want to build a new facility. With a new facility, we can extend the reach. We can make more neutron-rich isotopes and extend here to the right so that we can actually reach the nuclei that matter most in the art process. And for this, we're building a new facility. As I said, it's almost completed. We expect it in a little over a year to have first beams. So that's exciting. This is a facility that it's a project that is supported by DOE Office of Science and the state of Michigan and Michigan State University. And yeah, it's been going on for over 10 years now, and it's located right at the same location where we have the current lab, the NSCL. If you want to see a little bit of what that looks like, this is a video. I don't know if it's rendering fast enough, but you can kind of see the overview of the building. There's, instead of the 2 cyclotrons, we will have a linear accelerator, which you could see over there. The idea is the same. You get the initial atom, anything naturally occurring, anything stable. You can strip out the electrons from that atom, so you can accelerate it. Now it will be positively charged, and you can accelerate it. And once it's stripped and you just have the nucleus, it goes through the linear accelerator. It's here in a tunnel. It goes faster and faster. It's not going to go much faster than what we have right now with the cyclotrons. It's just more powerful. It will just have a lot more of the nuclei that we're interested in, and we'll also make new isotopes that we cannot make right now. We just don't have enough. Again, you shoot the stable beam through a target, and you have various reactions happening, and you can see that the things that are coming out will look very different. You just have that fragmentation again. And then you go through your filter, through the fragment separator, where if it's too light or if it's too heavy, they just get bent more or they get bent less. But the thing that you care about will go through the separator, through the magnetic field of the separator. It will go straight and go into your setup. And in case you didn't notice, right here, it was sun, actually. I used sun for the cool video here. And yeah, you guide it into different experimental stations to do your experiments. So this gives you an idea of what the experiments look like and the equipment and so on. Oops. Yeah, so I think I will stop here and just hope that you get a little sense of what it's like to do nuclear astrophysics, experimental nuclear astrophysics work. How do we choose our experiments? How do we run our experiments? And how our experiments are connected to the big questions about how the elements are made or any other astrophysical questions that we can contribute in. We have a lot of experiments happening right now at the NSCL, although it's right at the end of its life. So very soon we will stop the NSCL experiments and start the year-long switch over to FRIB. So that's an exciting time. And with FRIB, we'll have new capabilities. We'll be able to reach isotopes that we cannot reach right now. And so this is a very exciting time for our field. So for you guys, if you would join this field, for example, then in a few years when you're ready, you're in grad school and you're running first experiments with FRIB, this will be amazing. We'll be running things that no one else has seen before. So this is pretty cool. And so I'll just finish with the same information I had on the first slide and the websites of the lab and my information. And so just contact me if you have questions. Thank you very much.
Thank you, Artemis. Let's clap our hands. I always have a hard time finding the button.
Thank you, thank you.
Very nice presentation. So now everybody has a chance to brush up their score for the coffee mug competition. So are there any questions for Artemis? And you can just talk. We're a small enough group, that's okay. You're welcome to type into the chat. And I think you can email Anna, right? She's nodding, yes.
Yes.
So, are there any questions for Artemis?
Don't be shy. Can't be that everything is clear. There we go.
Okay, there's one question. So what element does your group focus mostly on?
So my group focuses on heavier elements, not one particular element. In general, anything from iron and above that we can access, then we do experiments. It's especially for the art process and for these heavier processes, there's thousands of nuclei that are involved. And so typically it's hard to find the one nucleus that you will go and you will measure this one nucleus and learn everything there is about this particular process. Typically you need to study several of them and try to get some kind of a sense of how things behave, how these nuclei behave as in a particular mass region. So we try to go to mass regions. And so recently my group has been focusing around mass 70. We did a lot of experiments with nickel, neutron-rich nickel, nickel 68, 69. We went through nickel 74. And just in general, copper is in that mass region as well, and just trying to get a sense of how nuclei behave in that region. And then you can work with your theory colleagues to try and reproduce that region as well as possible. And then we try to go to different mass regions and try to cover the chart.
Okay, and here's another question. How can theorists assist the experiments?
Yeah, that's theory and experiment go hand in hand. And the way I see it is that sometimes one is ahead and sometimes the other one is ahead, and you can never know how this goes. So sometimes a theorist will make a prediction and say, okay, I predict that this is what this new nucleus should look like, but experiment hasn't reached there yet, so we don't know. And finally, the experiment gets there and measures that quantity. And sometimes we agree with theory and we are all happy, okay, yes, we did it and we're in agreement. But it's usually more interesting if we go there and we don't agree, and then we all have to sit down and figure out, why do we not agree? What's the new physics that's there that we were missing in the original model? But also sometimes the experiment will go one step further and measure something that there's no prediction yet. And so then theory has to come back and say, okay, oh, this is what you see, let's try to describe it. And so we go together. There's a lot of nuclei, especially in nuclear astrophysics, that cannot be measured experimentally. So we definitely have to rely on theory to predict all these properties. And that's again where we have to work together to kind of benchmark the models and say, okay, I cannot measure all 2,000 nuclei, but maybe I can measure a few and compare to the models and say, oh, yes, they work, or no, they don't work.
Okay, are there any more questions? I don't see anything in the chat. Well, if not, you're also welcome to contact the speaker.
Anytime.
For example, if you watch this offline. Hey, there's one more question. Do any of the nuclei yeah, does the I paraphrase it. I hope that's it. Well, no, actually, I should just. Well, I'll paraphrase it. I think the beta gamma radiation from the nuclei, does it breach the lining of the cyclotron? I think it's a.
So,
if you're there, Angela, if you want to say something, feel free to clarify if I didn't get it right. Okay.
No, I think you got it right. I was asking if any of the radiation was escaping from the lining of the cyclotron. Mm-hmm.
So when we run our experiments, all the equipment and all the experiments are done behind very thick walls. We have these 6-foot thick walls, and actually doors that are this thick as well. And it's quite impressive to see those doors close and everything. All the beam is on the other side, and experimentalists are sitting on the outside. There is, especially with the cyclotrons, there is radiation coming out in those regions. Of course, we do our experiments in a safe way. No one is sitting there when the experiment is happening. When we go all the way to the experimental stations, the experiments we do are done with the most exotic, the most rare isotopes. So there's typically very few of them that actually make it into your detector. So all the way to the other end of the lab where we do our experiments is not that much radiation. But in the beginning, you have to start with as many as possible, so you have a chance to even create these most rare ones. So yeah, on the cyclotron side, there's definitely radiation that escapes the beamline or the cyclotrons themselves, but it's all done in a safe way because all shielded behind thick wall.